So for the next one, if you're going to multi-step, let's disregard what's given right now, and let's say that step 1 is the slow step. How would I find the overall rate?
This is an A plus A. So it'd just be K times NO to the second.
Yeah. Right, because this is a bimolecular reaction. There's 2 of these, so therefore it'd be this. But you know that this isn't the case because this one's the fast one. So if we go to the slow, we're gonna have to use
KN2O2 BR2.
Yeah, we're gonna have to use our knowledge of what equilibrium is. So in this case, I'm always just gonna first just copy my reactants and their corresponding coefficients as my rate of reaction. So the rate of my reaction is just the concentration of N2O2 times the concentration of Br2.
Yeah.
In this case, I'm going to put it in terms of K2. So the reason why I'm using a subscript of 2 is just to identify my different Ks. I'm not using just a K because I know that this isn't my final rate law because I have a intermediate.
Yeah, it's just gonna end. You're not gonna be able to measure it because it disappears so fast.
Right. So what I'm gonna do is I'm gonna identify that my rate of my first reaction is the same as the rate whenever it goes back. So the forward and backwards motion of my first reaction would be the same.
Yeah.
Right. So even though the rates are the same, the rate constants are going to be different. So I'm going to identify my rate constant for my first rate as K1, for my second rate as K
-1.
Inverse 1 or -1, yeah. So for my first one, since I have two NO molecules going and creating an N2O2, it'll just be K times NO squared. Right? Whenever it goes backwards, it'll just be K -1 N2O2, and there's no exponent here as it's a unimolecular reaction.
Yeah.
Now to tie it all together, I can solve for my N2O2, and I can say that my concentration of my N2O2 is found whenever I take my rate constant of the first equation of the first synthesis, right, times my concentration of my NO squared, as it's a second order reactant, all over my rate constant for the decomposition of N2O2, right? That'd be K1 times NO, yeah. And now that I know what my concentration of N2O2 is in terms of, with only constants and initial reactants, what I can do, I can say my entire rate of my reaction is just K2. I don't know why it's floating. It would be K2 times, so if I substitute this in for the concentration, these can just be considered as like one big variable.
Yeah.
Right?
Yeah.
It'll just be K1 NO2 all over K inverse 1. And don't forget, I still have to bring my BR.
Yeah.
2. Now I can simplify. I can say that my rate of my entire reaction is my reaction constant for the second one times my reaction constant for the first synthesis over my reaction constant for the first decomposition times my concentration of NO squared times BR2. And finally, I identify all of these are constants, but for different reactions. K2 is the constant for the slow step. K1 is the constant for going from NO to N2O2, and K inverse 1
is the constant going back from
N2O2 back to NO. So my overall rate constant is if I multiply these two and I divide by this. So this entire part can just be called K. And then of course I'm going to pull down my NO squared and my BR squared, or my 2BR.
BR. Yeah. That's because of no math in and of itself, right? You just see a bunch of constants, you just combine them into one big constant.
because I know like conceptually that the rate constant will just be all these different rate constants combined, because that's how the math worked out. The question states that we know, based off of a previous part, that our rate constant is k NO2 squared.
Yeah.
Right? That's our known. If we're given
Yeah.
a step 1 is it's a different color. If we're given that our step 1 is NO2 plus NO2 yielding NO plus NO3, and our second step is our NO3 yielding NO plus O2, right?
Yeah.
This is the slow step, and this is the fast step.
Mm-hmm.
If I'm writing on my rate, I'll just say my rate of my reaction is just my constant K times, well, this is, since this from the slow step, I'll count how many molecules I have. I have 2, so it'll just be times the concentration of NO2 squared.
Weird. Yeah.
This matches this, so this is a feasible mechanism.
Oh, okay. So you just have to see if it matches.
Yeah. So like the second one's a bit more involved. You have NO2 plus NO2 is in equilibrium with N2O4, our intermediate. Now N2O4 then yields to NO plus O2.
Oh, so I understand. So they'll
This is
give
my
you
fast.
a slow reaction and a potential fast reaction.
Yeah.
And they'll ask you if that potential fast reaction is a feasible reaction. Then you do all this voodoo magic to see if it ends up being the same. Do they call it molecular? No. What? No, it's not molecular. What's the freaking number?
Rate, right?
Yeah, the rate. If it has the same yeah, rate order.
Yeah. So like it has to have the same things in the concentration as well as the same order. In this case, if I call this 2, if I call it going back -1 and call it going forward 1, this would be my my K over here. I can
Yeah.
say that my rate of my overall reaction is represented by this rate constant times N2O4 to no exponents because they're just 1, but I want it in terms of my NO2. So
Mm-hmm.
what I'm going to do is I'm going to say that K1 of NO2 squared is equal to my K inverse 1 of N2O4.
Yeah.
And this should make sense as the rate of this happening is the same as the rate of this. So I just take this, count by 2, take this, count by 1, and they're the same.
Yeah.
Now, if I solve for my concentration of N2O4, I should be getting, I basically just divide this on both sides. So I'm just going to quickly do that.
Put
Right?
K inverse. Yeah.
And then I can say that my overall rate is just K2 times K1 over K inverse 1 times NO2 squared. And because I know that this is just the overall rate constant, I can just rewrite this as K NO2 squared. And this is consistent with this. So therefore, this is also a feasible mechanism proposal.